Okay, team challenge number 9 is very similar to what you did in the lab this week. So this is like the theoretical calculations that back up the experimental measurements that you did when you titrated amino acid. I just chose a different amino acid. To do the math for this, the first thing you always have to do is define how many moles are in one equivalent. So in the case of this team challenge problem, you got to imagine that you have a beaker and it's got, in this case, 40 milliliters of a 60 millimolar solution in it. So how many moles is that? That is 0.04 liters times 0.06 moles per liter. So this is equal to 0.0024 moles. So we have 0.0024 moles of lysine in a beaker. We're going to call that one equivalent. So it's 0.0024 moles per equivalent. Okay. We can do the calculations for this in a number of different ways. One of the easy ways is just to say, okay, how many milliliters of our 0.1 molar HCl make up one equivalent? So we say, okay, we need 0.0024 moles per equivalent, or moles to be our one equivalent, divided by the concentration of our strong acid or strong base. So this gives us 0.024 liters equals one equivalent. Okay? That is 24 mils. So 24 milliliters is equal to an equivalent. So we can then say 12 milliliters is equal to 0.5 equivalents, or 6 mils is equal to 0.25 equivalents, and so on. So to build your table where it has volume and equivalents of acid added and pH calculated, you simply say, okay, we have 6 mils, that's equal to 0.25 equivalents. Then we have to figure out what the pH is. Okay. When we add acid, we're starting at pH 7, and we're going to add one equivalent of acid because there's only one pKa for lysine. The pKa's for lysine, I looked them up in my own lecture notes. The pKa is 2.2, 9.0, and 10.5. This is the side chain here. So this is the amino group, and this is the carboxyl group. Okay? With 3 pKa. There's only one of them below pH 7, so we're going to take one equivalent to titrate down. We would naturally put the 2.2 at the half equivalent, and then we can fill in a number of points by calculating. So we'd say, okay, we started with the carboxyl group fully protonated, or fully deprotonated, sorry, A-. The carboxyl group would be in the A- form at pH 7. And so after adding 0.25 equivalents of acid, we would be in a situation of having 0.75 equivalents of A- and 0.25 equivalents of HA. The relevant pKa here is 2.2. So we can calculate the pH. You see I've been building up the Henderson-Hasselbalch equation here. We can calculate the pH of that by simply taking the log of this ratio, which is 3, and adding 2.2 to it. So in this case, that gives us a calculated pH of 2.68. So I would plot that in here as 2.68 and fill in a number of points there. Okay? Going in the other direction, we would need to add 2 full equivalents because I've got 2 groups with pKa's higher than pH 7. And so I would fill in my points at 0.5, that's easy. I'm going to be up here at the first pKa, and at 1.5 I'm going to be up here at the second pKa. And you can fill in a series of points using the same math that I just used. There's a little trick that happens here that some people found when they did this problem. If you get into the zone around one equivalent, I'm just going to mark it in here, what happens is you're going to calculate a point. Let's say we calculate the 0.95 point. So we've added 0.95 equivalents of OH. which means we would be in a case of, because this time we started with everybody fully protonated, we would be in a position of having 0.95 of A minus and 0.05 left of HA. All right? If we took the log of that ratio and added the pKa of 9 to it, because we're still, in a sense, titrating out this first group here, that would give us, I got to do the math, that would give us 0.95 divided by 0.05, the log of that, plus 9. I got a value of 10.1. I feel like that's wrong, but I'm going to check it. 0.95 divided by 0.05. Yeah, that is wrong. It's actually 10.3. I get a value of 10.3. So I can actually plug this in up here at 0.95. Problem is, if you then go and do 0.05 equivalents of the next pKa, you can say, okay, this next group was fully protonated when I started, and so now I've only got 0.05 A minuses and I've got 0.95 HAs. Take the log of that, add to it the new pKa, which is 10.5, and I think you're going to find that things go a little screwy here, because we get 0.05 divided by 0.95, take the log, add to 10.5, and now we're at pH of 9.22. So whoops, what the hell happened there? We were going along on a nice titration curve that looked something like this, and we did that. Whoops, that's bad. What is happening here? What's actually happening here is that before, sorry, that's a really crappy drawing, before we finished titrating out the amino group on lysine, the side chain amino group on lysine started to deprotonate. So it's like these two groups are overlapping in their titration curves. If you did the math to figure out how much of this group would be deprotonated at 10.2, you'd find that most of it, or a little less than half of it, was already deprotonated. So in a sense, what's going to happen here if you do this experimentally is you'll find like an average of those different two pKa's. Not to worry, this is perfectly correct to calculate this and see it. I just want to warn you that it's not as simple as doing all of the pKa's in order. In real life, we get a number of different species happening here. But I just wanted to point out that that was possible. So that's how you do this problem. You figure out the number of equivalents at each volume that you choose and apply the Henderson-Hasselbalch equation to give you a calculated titration curve.